Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, New St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind adjust the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, New St. Augustine.
At the Christ the King College, Onitsha, of the then East Central State of Nigeria of 1970, I was the rising star in physics and calculus. For that reason, everybody at Christ the King College, Onitsha, called me Calculus rather than Philip. At Christ the King College, Onitsha, my physics textbook was titled Advanced Level Physics. That physics textbook was co-authored by Michael Nelkon and Philip Parker. Those that knew me by the name Calculus at Christ the King College, Onitsha, Nigeria, we are not surprised that I won a scholarship that was dated September 10, 1973. That scholarship made it possible for me to arrive in the United States on Sunday, March 24, 1974. I spent my first night in the United States alone. I spent that first night in 36 Butler Hall, Monmouth, Oregon. An earlier turning point for me as a mathematician was in June 1970 at age 15 inside a bookstore near Dennis Memorial Grammar School, Onitsha, East Central State, Nigeria. The bookstore was a short distance from Zeke's Roundabout, Onitsha. Inside that bookstore, I paid the then unheard of £1.05 for a 568-page blue hardbound book that was titled An Introduction to the Infinitesimal Calculus. The calculus book was subtitled with applications to mechanics and physics. The calculus book was written by G.W. George William Count and published by Oxford University Press. The frontier of knowledge of physics, calculus, and algebra are the intellectual salts that I used in my supercomputer quest for the then uncharted territory now known as the massively parallel processing supercomputer. That terra incognita of knowledge is where the fastest supercomputer exists and where I discovered how to harness my ensemble of processors as the building blocks of a new supercomputer. That new supercomputer is the precursor to the modern parallel processing supercomputer. I discovered how to harness those processors to solve extreme scale problems in algebra that arose in computational physics. I was the first person to witness the world's fastest algebraic computation that occurred across a new internet that was a global network of 65,536 processors. I witnessed that fastest algebraic computations at 10:15 a.m. New York time, Tuesday, the 4th of July of 1989, the U.S. Independence Day. That experimental discovery represents a new paradigm in the history of algebra. At first, I couldn't believe my fastest algebraic computations, and I believed that I had made a mistake in the manner I operated the internal timer that I used to time the speed of my new supercomputer. Everybody said I had made an embarrassing mistake, but everybody was embarrassingly mistaken. At my mathematical core, I'm also an extreme scale algebraist. It made the news headlines in 1989 that I, Philip Emeagwali, discovered how to solve the largest system of linear equations of algebra and how to solve them at the fastest speeds but with the slowest processors. What I contributed to extreme scale fast computational mathematics was the cover story of top publications in mathematics. I discovered how to reduce the toughest problems in calculus to their acceptable approximations in algebra. I discovered those algebraic approximations as the most extreme scale problems in computational algebra. That mathematical discovery led me to the most computation-intensive problems in floating-point arithmetic that I could only solve by first discovering how to massively parallel process and how to do so across my small copy of the internet. That's a global network of 64 binary thousand processors. Let's put my mathematical discovery in historical perspective. The quadratic equation of your high school algebra had one unknown and two solutions, just as the quadratic equation x squared equals 9 has the two solutions -3 and +3. And your high school small-scale algebra textbooks didn't go beyond a system of 3 equations that had to be manually solved for 3 unknowns. But today, I am wondering, how can I massively parallel compute a system of 1,000,000 billion trillion equations of algebra and do so to compute at the fastest speeds for answers that comprise of knowing 1,000,000 billion trillion unknowns? That's impossible to scribble across all the blackboards in the world. That's impossible to store within one motherboard. I discovered that massively parallel supercomputing may make it possible to someday solve for 1,000,000 billion trillion unknowns and help discover and recover otherwise undiscoverable and unrecoverable oil and gas. More than half of the oil and gas discovered in Nigeria are unrecoverable. Around the world, thousands of oil fields have been abandoned because more than half of the oil and gas are unrecoverable. The Oloibiri oil field of the Niger Delta region was Nigeria's first oil field. The Oloibiri oil field was discovered in 1956 and began production in 1958. The Oloibiri oil field was abandoned in 1978. The Oloibiri oil field was abandoned 20 years after it was discovered. The Oloibiri oil field was abandoned with about 70% of its oil and gas deemed unrecoverable. My application of extreme scale algebra in extreme scale multi-physics scenarios of petroleum reservoir simulation is the most important application of algebra in Nigeria. Algebra is an instrument of poverty alleviation. In the early 1990s, I gave lecture tours across the United States that sparked new interest in massively parallel processing supercomputers. My parallel supercomputing lectures were co-sponsored by the Association for Computer Machinery, that was the premier society for computer professionals. My parallel supercomputing lectures were co-sponsored by the Computer Society of the IEEE, that was the largest society for computer professionals. Although I gave 90-minute lectures in the early 1990s, I must say that my experimental discovery of how parallel processing makes computers faster and how parallel processing makes supercomputers fastest cannot be passed along in a 90-minute lecture. My experimental discovery took me 15 years onward of June 20, 1974 to discover. Therefore, it should also take you 15 years to rediscover the parallel processing supercomputer that took me 15 years to discover. It's often said that it takes 10,000 hours to become the best athlete, to become a professional soccer player, to become a tennis professional. I put in 200,000 hours to experimentally discover how and why massively parallel processing across a new internet makes the supercomputer super. Any person that did not put in 200,000 hours cannot explain how I invented the modern parallel processing supercomputer. For me, Philip Emeagwali, the 1970s and 80s were the decades of darkness. In those decades, mathematicians ridiculed me by saying, "This will not work." Looking back, those rejections paved the way for me to work alone. It was important that I pursued only my own scientific vision. Two bad visions are not better than one good vision. Two heads with two visions are not better than one head with one vision, unless both heads pursue only one vision. Put differently, democracy rarely works in the quest for new scientific knowledge. As the inventor, I alone know the origin story of my invention. I know how I want to express my story. I don't care if my expression conforms to how others expect me to express it. Nobody should be afraid to be who she is. In the United States and Europe, and in the 1970s and 80s, the leaders of thought in the world of supercomputing, namely Gene Amdahl, who advocated sequential processing supercomputing, and Seymour Cray, who advocated vector processing supercomputing, had the wrong visions for the future of the supercomputer that will be parallel processing and doing so across an ensemble of millions of processing units. In the early 1980s, I was mocked and dismissed from my research team and ridiculed when I told teachers to stop teaching sequential processing supercomputing and to stop teaching vector processing supercomputing and to stop teaching both techniques and technologies as the only paradigm in supercomputing. The supercomputer textbook authors and the supercomputer teachers of the 1980s and earlier didn't understand how to parallel process extreme scale problems in computational physics. If they did, they would not have incorrectly dismissed parallel processing as a huge waste of everybody's time. In Google, a popular search question is, who is Philip Emeagwali? I was born in the late afternoon of August 23, 1954, in Akure, in the heart of Yoruba land, in the then British West African colony of Nigeria. I'm studied in the United States, where I reside, but I'm not studied in Nigeria, where I was born. In fact, it's easier to study Nigerian contribution to technology in US schools than it is to study Nigerian inventions in Nigerian schools. My Igbo-speaking parents, Nnemeka James and Inyamma Agatha Emeagwali, were born and raised in Onitsha, colonial Nigeria, and lived briefly and independently in Kano, Nigeria of the late 1940s, and both speak the Hausa language. Who is Philip Emeagwali? I am the research massively parallel processing computational mathematician that discovered how to reduce the abstractions of mathematics to 65,536 computer codes that I synchronously emailed across what I visualized as a small copy of the internet. That's a global network of 65,536 processors. I am the research massively parallel processing computational mathematician that discovered how to make computers faster and make supercomputers fastest. I am the research massively parallel processing computational mathematician that discovered that what formerly took 65,536 days or 180 years to compute could now be computed in just one day across a new internet that's a global network of 65,536 processors, or across as many computers. It's often said that mathematics is the queen of sciences. I said that the partial differential equations of modern calculus is the crown jewel of modern mathematics. The partial differential equation is the most advanced and the most important expression in calculus. The partial differential equation was my first tour de force into modern calculus. On July 8, 1991, in Washington, D.C., United States, I delivered a pivotal lecture at the International Mathematics Congress called ICM 91. At that Mathematics Congress, I lectured on the system of 9 coupled nonlinear and time-dependent partial differential equations of modern calculus, called Emeagwali's equations that I invented. The partial differential equations of calculus and their companion system of partial difference equations of algebra that approximated them are used from the construction of the tallest buildings in Lagos, Nigeria, to the construction of the second bridge across the River Niger at my ancestral hometown of Onitsha, Nigeria. In the 21st century, Africa must cross new frontiers of technological knowledge to conquer today's challenges. One of those new frontiers is the mathematical knowledge behind the parallel processing technology that makes the computer faster and makes the supercomputer fastest. The partial differential equations of modern calculus and its companion partial difference equations of large-scale algebra play an invincible but pivotal role in Africa's economic development. In the Niger Delta region of my country of birth, Nigeria, a detailed geological survey that included high-performance mathematical computations that were executed across an ensemble of processors was necessary to discover oil and gas that was buried 1 mile deep and buried in hard-to-discover places. The 81 partial derivatives that defined my 9 partial differential equations of modern calculus are symbolic representations of the inertial, pressure, viscous, and gravitational forces that govern the unseen subterranean motions of oil, water, and natural gas within the oil field. On my blackboard, these 4 forces are only visible to a few dozen people that were initiated into the mathematical priesthood of the system of partial differential equations that was at the calculus core of petroleum reservoir simulation. As a physicist and as a mathematician, I had to concretize my abstract calculus to physical forces. As a lone wolf massively parallel processing supercomputer programmer, my grand challenge was to experimentally discover how to make the previously impossible to compute possible to compute. In the 1980s, I had 64 binary thousand processors and had them in the decade it was considered impossible to use them to achieve a speed up of 64 binary thousand. That speed up that I achieved in high performance supercomputing is the equivalent of reducing 180 years of time to solution on only one processor that was not a member of an ensemble of processors to only 1 day of time to solution across an ensemble of 64 binary thousand processors. To perform my mathematical magic, that was the cover story of the May 1990 issue of the Siam News. That was the top publication of record in mathematics. Required that I get the correct mental picture of how to perform the magic and perform it across a new internet that I visualized as my global network of 65,536 processors that were married together as one seamless cohesive supercomputer that was married together by 16 times as many, or 1,048,576 commodity email wires. I was the magician that made the invincible visible. I had to make the invincible 65,536 initial boundary value problems of calculus visible as 65,536 global circulation models, or visible as 65,536 petroleum reservoir models. I was the magician that made the invincible 2 to the power 16 email messages that I sent to as many 16-bit long addresses and made them visible at the as many vertices of the cube in a 16-dimensional universe. My lectures to research mathematicians were for experts who liked their mathematics uncensored and preferred matrices, tensors, and summation indices over words. My lectures to research physicists were for computational physicists who like their fluid dynamics raw. Here is a 3-minute version of my lecture of July 8, 1991 in Washington, D.C. that I delivered at the International Mathematics Congress that was the largest gathering of mathematicians ever. As an aside, the mathematical sophistication and the computational complexity of the extreme scale high resolution petroleum reservoir simulator has grown exponentially since the early 1950s. The oil and gas industry massively parallel processing supercomputer codes are proprietary. Those supercomputer codes are classified as trade secrets. For that reason, I do not have the liberty to share the petroleum reservoir simulation codes that I analyzed in the 1970s, in the 1980s. From analyzing actual production codes, I mathematically discovered that petroleum reservoir simulation codes are used with critical mathematical defects. I mathematically discovered that the system of coupled nonlinear and time-dependent partial differential equations of modern calculus that governs the initial boundary value problems that defines the mathematical core of petroleum reservoir simulators are defective. I mathematically discovered that they are defective by 36 partial derivative terms. Those mathematical defects, comprising of 36 partial derivatives, were replicated across the finite difference algebraic approximations of the continuous initial boundary value problems, and the mathematical errors that occurs in the extreme scale algebraic approximations were in turn replicated across the computer algorithms that was used to code the solution of the system of finite difference algebraic equations. In a mathematical nutshell, I contributed to the modern calculus that is used to discover and recover otherwise undiscoverable and unrecoverable oil and gas. I, Philip Emeagwali, pushed the frontiers of the partial differential equations by reducing it to its algebraic and arithmetical equivalences and coding it to its floating point arithmetical operations equivalence and executing those arithmetical operations across a small copy of the internet. I pushed the frontiers of calculus and algebra on the blackboard by inventing new calculus and new algebra. I pushed the frontier of arithmetic on the motherboard, experimentally executing the fastest arithmetical computations ever, and by emailing them across an ensemble of motherboards. I pushed the frontier of calculus on the blackboard and pushed it by a distance of 36 partial derivative terms that I invented to be used to recover otherwise unrecoverable oil and gas. But I mostly pushed the frontier of calculus across my small copy of the internet that I discovered is a global network of 64 binary thousand processors, or a global network of as many computers. At the International Mathematics Congress, I was cognizant of the fact that, unlike the pure mathematician, I am a physicist and a supercomputer scientist. And as a scientist and a technologist, I had to distinguish between a scientific discovery and a technological invention, and the burden of doing so for a mathematical community that we are unsure if my 9 previously unseen system of coupled nonlinear and time-dependent partial differential equations called Emeagwali's equations for all that flows underneath the surface of the earth should be classified as a discovery or as an invention. A method for solving partial differential equations may be a discovery in mathematical physics, but is not by itself a discovery in physics per se.
Insightful and brilliant lecture.